Hello everyone, we'd like to present our joint work with Oleg Vetrov, Olha Trofimenko, Vera Trofimenko, and Maxim Friharov about the methodological aspects of studying the accuracy of computer calculations in applied problems. So the goal of this study is to examine some examples of computer calculations that are completely correct in terms of computer standards for handling numbers and arithmetic operations, but at the same time, the result is incorrect from the point of view of human implementer. The problem that can appear due to incorrect representation in computer memory are well known, and sometimes there are problems that do not have a significant impact on a qualitative sense on a particular outcome. Therefore, in applied activities, software developers, as well as academic researchers, often do not pay attention to the problems of floating point calculations and the features of the IE 754 standard. However, there are cases where careless handling of the computer representation of numbers has led to the serious tragedies. Let's give just two examples. On February 25, 1991, during the Gulf War, an American Patriot missile battery in Tehran, Saudi Arabia, failed to track and intercept an incoming Iraqi Scud missile. The Scud struck an American Army barracks, killing the 28 soldiers and injuring around 100 other people. Report turns out that the reason was in an accurate calculation of the time signs boot due to computer arithmetic errors. Specifically, the time in tenths of a second, as measured by the system's internal clock, was multiplied by 1/20 to produce the time in seconds. This calculation was performed using a 24-bit fixed point register, and in particular, the value 1/10, which has a non-terminating binary expansion, was chopped at 24 bits after the radix point. The small chopping error, when multiplied by the large number given the time in tenths of a second, lead to a significant error. Indeed, the Patriot battery had been around 100 hours, and an easy calculation shows that the resulting time error due to the magnified chopping error was about 0.34 seconds. On June 4, 1996, an unnamed Ariane 5 rocket launched by the European Space Agency exploded just 40 seconds after its liftoff from Kourou, French Guiana. The rocket was on its first voyage after a decade of development, costing $7 billion. And the destroyed rocket and its cargo were valued at $500 million. A board of inquiry investigated the cases of the explosion and in 2 weeks issued a report. It turned out that the cause of the failure was a software error in an inertial reference system, specifically a 36-bit floating point number related to the horizontal velocity of the rocket with respect to the platform was converted to a 16-bit signed integer. The number was larger than 32,768, the largest integer storable in a 16-bit signed integer, and thus the conversion failed. So this literature describes other examples where, as a result of ignoring some specific computer calculations, the exchange suffered losses and the electronic voting system produced an incorrect result. Since one of the goals of the presented paper is to methodically study with students the features of applied work with the format of representing floating point numbers, it's appropriate to recall the fundamental works of the classics of the described subject, William Kahan and Jean-Michel Muller. And you can see the cover of the first edition of Muller's classical work, Handbook of Floating Point Arithmetics, on this slide. And one man might note a thorough review article by Muller published in 2023 in the journal Acta Numerica. And link can be found in our work. The rest of the books on the topic presented on the slide can also be useful in learning the basics of working with floating point numbers in IE 754 format. The problems with floating point numbers can be specific, and you can see some examples on this slide. And these problems require a deeper understanding of the features of the IE 754 standard, including the use of specific mathematical tools. While the IE 754 floating point format is the dominant format, it's not without its drawbacks. So studying existing alternatives, for example, the Unum computer methodology, can be useful for preparing the IT specialist. So you can see the floating point numbers according to the IE 754 standard are presented in the form where S is a number sign, M is a mantissa, E is a number order exponent. And figure shows the distribution of bits of a single precision number in the binary 32 format. The most significant bit is a sign, and the order of the number is preserved using the 8 bits. And 23 bits are allocated to the mantissa, a total of 32 bits. And below you can see an example with a mathematical point of view of 1/3 of a number in computer memory. And obviously it's different from its mathematical form. And due to the limited computer memory, it's possible to represent only a finite number of real numbers in the form of a finite decimal fraction. And this representation in most cases will differ from the original ones. And as you see on the slide, there is a well-known example from popular culture. Homer Simpson finds some counterexamples to Fermat's theorem. And if you use a standard calculator to check, the equality seems to be true. And this is again an example of the overflow problem and the problem of checking, proving some propositions. And below on the table, you can see more examples of Homeric numbers constructed by the authors for the int 32 types 4 bytes. On the next slide, you can see the restrictions on number data types, both integers and floating point in the NumPy model in a Python programming language. Looking at the tables, the prospects of the computational problems of loss of precision and numerical overflow become obvious. So the paper presents the several problems that, in the author's opinion, are methodologically useful in studying problems associated with the incorrect operation of a computer program due to the specific of working with the floating point numbers. And next, we will limit ourselves to considering a few specific examples when incorrect calculations give an acceptable answer that is mathematically correct, but doesn't satisfy some additional conditions of the problem. An example of is the optimization problems. We can find a value that will solve the problem, but at the same time does not satisfy extreme conditions. So it's necessary to find the minimum value of the parameter n that satisfies the proposed conditions. And you can see on the slide a simple example that can be easily solved in integers. But you can also solve this example directly by calculating values in the float numbers. It can be observed that the accuracy of 16 and 32 bits does not allow obtaining a correct answer at all. The correct value for n is, in this example, would be an 6,545 and is achieved with the precision of 64 bits. It's interesting that by increasing the accuracy to 80 bits, we get the correct pair. N is 6060 and M is 3060, 30. But N is 6060 is greater than N 4545. And with a greater accuracy, we get an incorrect solution for the problem. The situation that the computer calculations will be even more interesting if in the example, the value 2020 is replaced by 10. The correct answer in this case N is 30 and M is 15, and the accuracy of the calculation still needs to be guessed. The minimum recommendation in such cases is to check the numbers not for an exact match, but for the proximity of the values. And in Python, the isClose function from the math module serves a similar purpose. And finally, the most interesting example is a Muller sequence, and it's necessary to find a solution to a second-order nonlinear recurrence equation under the given initial conditions. And we want to note that mathematical research shows that this sequence can converge to only one of three cases, to the value 5, to the value 6, or to the value 10. And the software implementation is very simple. From a mathematical point of view, increasing the numbers of iterations should automatically increase the accuracy of the calculations. But as we can see, the number of iterations increases and the accuracy decreases, and in the end, it comes to a value of 100. Also acceptable solution to the recurrence equation, but for the different initial conditions. And note that if we minimally change the initial conditions of the example, the result of the calculations will already become correct. So this problem was studied in detail by the authors in previous publications with mathematical and computer calculations. So conclusions. The topic of correctness for the computer calculations in the training of IT professionals is extremely relevant, but in our opinion, not sufficiently covered in the Ukrainian scientific and scientific pedagogical literature. And according to the experts, it's important for students that examples of incorrect calculations are not just specify adapted examples in specialized areas. Cases of incorrect calculations can occur in the simplest tasks at first glance, and the results of the calculations may seem paradoxical. We can recommend the special tools for monitoring the accuracy of calculations shown on this slide, the decimal and factorial models, for detailed consideration not only for the students and the future professionals in engineering or modeling, but also for all IT professionals. And also there is a separate consideration for the preparing each MP Math module. MP Math is a free Python library for real and complex floating point and arbitrary precision arithmetic. So thank you everyone for your attention, for your time.